All right. Okay, thanks a lot for inviting me to give this talk. Sorry that I couldn't be there in person. So since this is the last talk of the day, I will not try to overwhelm you with information and just sort of try and present a new way of approaching jet physics in heavy-ion collisions using the idea of factorization. Um, so, so the basic question that we all are interested in is that we want to probe a strongly coupled medium because we know that in current heavy ion collisions, the quark gluon plasma that's actually created is a strongly coupled fluid. So the temperature achieved is of the order of a few hundred MeV, where it's shown that this is actually a strongly coupled fluid. So we really cannot describe it reliably using perturbation theory. Um, you can say that hydrodynamics has been really successful in explaining some of the properties of this QGP, but hydrodynamics is an EFT that usually works on longer length scales. What we are interested in is actually probing the microscopic structure of this quark gluon plasma using high energy jets. Of course, there are other non-perturbative techniques to deal with this strongly coupled medium, which are the holographic techniques. However, since those usually yield qualitative results because there is no real direct proof that there is a dual to QCD. And so in that sense, we cannot really say that they're systematically improvable in the sense that they cannot move us systematically towards QCD in any expansion parameter or anything like that. So in that sense, the question still remains that how can we actually make precise predictions in this heavy ion collision environment where we do have this strongly coupled medium. So even though I'm mainly going to talk about heavy ion collisions in this case, this is a generic problem, which is also very similar to two other problems that I would like to highlight, which is in this case, a jet propagation in cold nuclear matter, which usually happens in heavy nuclei, for example, in the electron ion collider. You can also have DIS at small x, which is a very similar problem again, except there the probe is sort of a QQ bar pair, which is probing your nucleus. So in each of these cases, we have some type of probe, either a jet or a dipole, which is probing a strongly coupled medium, and we want to describe this using in a non-perturbative way. And the reason they are similar because in each of these cases you have an extended medium. It's not like a small medium. So the point I want to make in this talk mainly is that this is not a new problem in physics. We have been dealing with non-perturbative physics for a long time in hadronic colliders. In that case, for example, you have a strongly coupled initial state, for example, a hadron, which again cannot be described by perturbation theory. And yet, in those cases, we are able to make precise predictions for all sorts of observables, which are relevant for both QCD and BSM physics. So here, for example, you have the classic DIS experiment or the Drelian experiment at the LHC. And the key point here is that both of these rely on the idea of factorization in order to be able to make any sort of reliable predictions. And that's what I'm going to be sort of focusing on for the rest of this talk. All right, so I'll just go through a familiar examples. These are very familiar examples to most of the audience here, but I would like to sort of drive home the point as to why we need factorization before I move on to the case of heavy ion collisions. Now, the first important thing is any kind of factorization relies on a separation of scales. For example, in the case of DIS, you have two scales in the problem where you have a high energy electron, which is probing, say, a proton. Then you need that in order to probe sort of the microstructure of the hadron, you need that the photon have a large momentum compared to the inverse Compton compared to the Compton wavelength of the hadron. So in this case, the photon momentum Q is sort of a large scale, which I will call as a UV scale, whereas the IR scale in the problem is just the scale of the mass of the hadron, which is in this case is lambda QCD. And in this separation of scale regime, we can sort of write down a factorization theorem, right, for the cross section in this process, which is just an inclusive cross section. And the cross section can be written in a very simple form in which it factorizes in terms of Hart function that sits at a UV scale and hence is perturbatively calculable, and a parton distribution function which sits at the scale lambda QCD and in general is non-perturbative, and hence it's very hard to compute it analytically. And this sort of separation works at leading power in our power counting parameter, which is basically the ratio of the two separated scales in our problem. So that's the general idea of of factorization in hadronic colliders. And what this gets for us is that by factorization, what I mean here is essentially is that the degrees of freedom at this UV scale Q are no longer interacting with those at lambda QCD. So in that sense, these two functions, H and F, can be computed independently of each other to all orders in perturbation theory. So what this also gives us is an explicit separation of perturbative and non-perturbative physics. So far so good. We have a separation of perturbative and non-perturbative physics, but we still don't know how to calculate this because F is non-calculable in general analytically. But the main power of factorization is that it gives us predictive power via universality. So if I consider an analogous process, for example, in for the Drelian process at the LHC, where I have two protons, which are creating a lepton pair with an invariant mass of order m, then as long as the scale m is again well separated from our lambda QCD scale, this again allows us to write down a factorization theorem for the cross section. And this cross section again appears very similar to the case of the DIS, where instead of where I have a different Hart function now, which sits at the scale m, but is still perturbatively calculable, so it's under our control. But I then have two copies of the parton distribution function, which is the exact same function that appears in DIS. And that's where the universality comes in, that we can sort of extract the PDF from DIS and then use it as an input to make predictions, even though it's not actually calculable and it is non-perturbative. And again, this factorization is valid to leading power in my expansion parameter. So in that sense, you can think of the PDS as an object which isolates some universal information about the strongly coupled initial state, because as you can see, it's independent of the exact process that the proton is involved in, or in fact, independent of what exactly I'm measuring in the final state. So in that sense, I mean that it is a universal quantity about the structure of that hadron. All right. So apart from this obvious utility of factorization, we have some other really interesting things that it gives us, which are really useful for analysis. So first of all, apart from proving factorization in terms of this universal function f or a PDF, we also have an operator definition of the non-universal physics, of the universal non-perturbative physics. So in this case, for us, it's the PDF. And as we know, the PDF is simply a quark bilinear, a gauge invariant quark bilinear along the light cone, which is evaluated in the background of the density matrix of the hadron. And no matter what the hadron is, the operator definition is essentially the same. So the great utility of this operator definition is that it's a standalone matrix element in a hadron state, and which is why it is way easier to compute numerically on a lattice or quantum computer. I think this was I think related to what was mentioned in the previous talk as well. And it's much easier to do than actually a full simulation. So that really saves us a lot of trouble by using factorization in this manner. Obviously, since I have an operator definition, the one loop or radiative corrections that can be done have to be done only once, since they are the properties of the operator and not of the state or even of the process, right? So this thing has to be done just once. In this case, for example, for the PDF, it's the T-Glab equation. Now, once we have those RG equations, we can enormously improve our numerical predictions by simply resumming logarithms by solving these RG equations that come from renormalization. In this case, for example, you just have two functions. One is the PDF and one is the Hart function, which are separated in scale. And the renormalization group equation in this case, or the RG equation, is just dglab, which you can solve and resum any logs. In this case, the logs are of the form of alpha log to the alpha log of Q or lambda QCD. So basically the logs of your power counting parameter. And last, but most importantly, this sort of formalism is systematically improvable. By that I mean is that whatever perturbative functions you have in your calculation, they can be computed order by order to in perturbation theory independently, because it's factorized. And second, to improve the predictions further, we can include higher powers in the expansion parameter, which in this case is just the ratio of the separation of the two scales. So now, given all of these advantages, let's now come to the problem that we really care about, which is that of jet production. So before I go on to actually heavy ion collisions, I want to sort of present what the factorization would look like for jet production in PP collisions, which is sort of the baseline for comparison with heavy ion collisions. So in this case, the process we are interested in is PP creating a jet plus anything else. So it's an inclusive jet production. And we want to sort of measure the cross section for creating a jet of radius r and with the total PT, total value of transverse momentum equal to PT. So if I again look at the scales in the problem, I again have my jet PT, which is the largest scale in the problem and is sort of the UV scale of my process. Then again have my scale lambda QCD as the IR scale. But in this case, for small radius jets, which is what I'm going to focus on here, I also have an intermediate scale, which is PT times R. And that sort of sits between my UV and IR scale. So I have like sort of a hierarchy of 3 scales in this problem, which I have to deal with now. So once again, I do have a separation of scales, and one might imagine that we can again appeal to factorization and be able to sort of separate out the physics at these separate scales in a systematic way, expanding in our ratio of scales again. So here's what the formula looks like, and this was sort of presented in 2016 by Felix and Zhongbo and Ivan. And here's what the cross section looks like. So the cross section again is factorized in terms of 2 copies of our parton distribution function, which are again universal. So they are exactly the same as that appeared in DIS and Valian. So again, we have universality and we don't never need to calculate them again. You have a hard function, which sits at the scale PT, which is the UV scale of our problem. And again, is perturbatively calculable. And then I have a new function here, which is basically the jet function. Now the jet function again sits at the scale PTR, which is the intermediate scale. But since it is still larger than lambda QCD, this function is still perturbatively calculable. And as for any function in our factorization, we can go ahead and look at the radiative corrections for this function. And in this case, this jet function obeys a very simple equation, which is just the time lag deglab equation. And again, while proving this factorization, we have relied on the fact that we have a separation of scales. And we are expanding in this case in 2 parameters because we have 3 scales in the problem. One is the radius of the jet, which I'm assuming to be small, and the other is our usual IR over UV scale. So in this way, you see how we can systematically derive factorization theorem for this kind of processes, even for jet functions, or even for jet observables. And this is maybe the simplest jet observable that you can think of, which is just the probability to produce the jet with a given PT and R. That's all. All right. So now that you have seen how factorization in general works for hadronic collisions in vacuum, now we want to address this question, which is, can we actually do the same for jets in heavy ion collisions? And I would like to sort of affirm that, yes, we can do this. And that's what I'm going to talk about. Okay. So once again, we are looking at the same process, which is producing the jet with a given radius and PT, along with anything else. But now in a heavy ion collision environment. So let's again, following our strategy, let's look again at the scales in the problem that we have. We have the added complication of there being a medium through which the jet has to travel, and we have to see where the scales of the medium come into play. So obviously, we again have our UV scale as the jet PT. We have our intermediate PTR scale, same as that of vacuum. Now, as I said, the medium that's produced in current heavy ion collision is strongly coupled, which means the temperature of the medium, or SD by mass, are very close to lambda QCD, so that these 3 sort of form again the IR scale of my problem. But in this case, we have an additional scale, which is basically the medium size, and that's usually longer than in terms of length, and so lower in energy compared to any of the other scales in the problem. So there is one more scale which lies below lambda QCD, which is the medium size. So these are sort of the obvious scales that we can see directly from the process kinematically. But there are 2 other scales that are really important in this problem, which basically appear because of the fact that the jet that we have, or the probe that we have, can interact multiple times with the medium. And this also has been alluded to several times before. One of them is just the formation and time of the jet. which is the energy over its transverse momentum squared, which in this case basically scales as 1 over pt times r squared. And the second, which is another emergent scale in the problem, is the free path of the jet in the medium. So I'll talk about where these two scales sort of fit in this hierarchy and how do they change the analysis of the problem that we're interested in. Okay, so now that I have defined the problem and the scales, now let's just look at what the factorization looks like. So for simplicity, for the purposes of this talk, I'm going to stick to the case of a dilute medium. It can be inhomogeneous, so that's an allowance I'm making. But for now, I'm only considering a dilute case. And I'll define what I mean by that. So let's look at what the factorization theorem for this looks like. So I have my cross section, and it's written in terms of several pieces. So I'll explain what they are. First of all, you have an integral over the medium. So y is a coordinate in the medium. And the result is essentially written in terms of the inverse Mellin transform of the vacuum cross section. And we already know how to factorize this and do resummation and everything for this piece. So that's well known. And then the medium effects are all encompassed in this factor of an integral over the size of the medium over lambda mean free path, which is again an expression which might be familiar to you guys who are working in this field for a long time. So roughly speaking, obviously the mean free path is, you can think of it as the average distance between interactions of the probe with the medium along the direction of the probe, which is why in this case it's pointing along the y minus light code direction. And this sort of equation gives you a complete cross section for the process that you want. So you can just, if you can predict this, you can calculate this object, you can just go ahead and measure it in an experiment. So what I mean by dilute in this case is obviously the fact that I have that the mean free path, which is sort of the emergent scale in the problem, is much larger than the size of the medium that the probe sees. And this is also referred to as the opacity expansion. So far so good. I haven't really told you what the factorization is in this case, so I'll come to that. We already know how to factorize the vacuum cross section in terms of several different pieces. But what about the piece here, which is the mean free path? Now, here's maybe the most important slide in this talk. And if you don't take anything away, you should actually only remember this, that this mean free path is basically associated with the jet transport parameter. And I will show you exactly how it is related to that. But the key point here is that the mean free path depends on the properties of the jet and the properties of the medium, right? So it's not simply a universal quantity which depends only on the properties of medium, but it also depends on the properties of the jet. In this case, y, it's pt and r. So I will claim that q hat, which is the jet transfer parameter, is not really a direct probe of the observable independent medium properties the way we have a PDF in a DIS process, because it also depends on the probe that you're using. And this is the next important statement I want to make, that we must actually factorize this object further to separate out what the universal physics of the medium is from the properties of the jet. And this is what the factorization would look like. So the mean free path essentially can be factorized in terms of three functions. Again, we have a single hard function which sits at this our UV scale, which is pt. We have a medium function which depends upon the properties of the medium, but is independent of the properties of the jet. And in that sense, it's a truly universal object. And I will call that as the structure function. And I have the jet function, which is a medium induced jet function, which basically carries all of the properties of the jet, in this case, R and PT and so on and so forth. And this factorization is valid to leading power in R square, again, which is our expansion parameter. Now, given this type of factorization, I can tell you what the Q hat might look like in the factorized form, because we define Q hat merely as the average transverse momentum gained per unit distance. So in that sense, it's the same objects here, except that I have a K-pub square under the integral, which then tells you what Q hat would look like in a factorized form. So this sort of, if you can think of this is sort of the main result of this talk, which is to say that the mean free path or the transport parameter can in fact be factorized into something which is independent of the probe and something which depends only on the local properties of the medium, which is this S medium function. And now you can imagine that for different observables, merely the jet function is going to change. We can make really elaborate jet substructure measurements on this. We could measure jet mass, we could measure the pronginess of the jets and all sorts of things. And this object here will not never change. It will always be the S medium. Only the jet function needs to be recalculated every time. Okay, so we can just like the PDF that we have for the DIS process, we can give a precise operator definition for this object as well. And it's written mainly as a trace of two currents, colored currents, in the background of the density matrix of the medium. So these two currents can be defined as a sum over quark and gluon currents. For example, the quark current is basically a gauge invariant quark bilinear. So S here are just Wilson lines. So in order to make this a gauge invariant operator. So this is sort of the analogous PDF of the medium that you can think of compared to the DIS process. And it depends only on the local properties of the medium and on nothing else. As with the PDF, we can do a renormalization group analysis for this object, and it turns out that it obeys an RG equation in rapidity, which is just the BFKL equation. All right, and the most intriguing part of this is that if you remember the two processes that are alluded to earlier on my first slide, which were essentially a jet propagation in a cold nuclear matter and the physics of small x physics in terms of DIS, it turns out this operator is exactly the same and in both cases and describes the medium in those two processes as well. And that can be rigorously proved using factorization. The only difference is that the density matrix is going to change. That's all. The operator itself is going to remain the same. So it will have the same renormalization group equations and everything is the same, which is why you see that there is a BFKL equation here, which also appears if you're familiar with even in small x DIS. All right. So once we have the renormalization group equations, we can actually systematically do resummation of all the large logarithms in the problem. So in case of DIS, if you remember, we just had two scales, which was Q and lambda QCD, and we had a renormalization group equations in the mu, which was sort of the virtuality. Here, the situation is a little bit more complicated in the sense that we have RG equations both in virtuality and in rapidity. And the equation in virtuality is just the running of the alpha running for this object here. And this is completely separate from the resummation that we already did for the vacuum piece. So that's there anyway. So this is on top of that. The equation, the RG equation in rapidity is just the BFKL, as I mentioned earlier. And what this does, the BFKL equation basically resums all of the logarithms in alpha is log of nu j over k perp, where nu j is sort of the scale that characterizes the jet medium. Now, what this scale might be is something I can discuss quickly. So this is where the other emergent scales in the problem come into play. Mainly that if we are actually in a long-lived medium, which is to say when the length of the medium, the size of the medium is greater than the formation time of the jet, then you can imagine that the jet that's created in the hard interaction has enough time to go on shell before it actually interacts with the medium. And in that case, the natural scale for the jet is just the PT of the jet. On the other hand, when the medium is short-lived, that is when the formation time is much greater than L minus, then you can imagine that there might be some quantum interference between the hard interaction that creates the jet and its subsequent interactions with the medium, which is why the scale, natural scale for the jet now depends on the size of the medium and is given by a combination of its PT, the length of the medium, and its formation time. So that's sort of where the size of the medium plays a role and the formation time plays a role, at least in this case where I'm treating it as a dilute medium. All right, so how much time do I have?
About maybe 5 minutes or so.
Okay, that's fine. I have a couple of slides. All right, so now let's come back to the original problem that we want to address, that we want to work in a non-perturbative medium. So where is the perturbative physics here and where is the non-perturbative physics here? So let's look at our expression for lambda inverse again in terms of these three functions, and let's look at where they sit in terms of the scales. So we had our hard function here, which sits at this UV scale PT. We had our medium function, a jet function, which were separated in rapidity, but were sitting at the same scale PTR. So what we have done so far is sort of integrated out all the physics at the scale PT in terms of this hard function and written an effective theory at the scale PTR. But this is still a perturbative scale, which so the jet function here is actually completely perturbatively calculable. The medium function, on the other hand, contains physics both at the scale PTR all the way down to the scale MD, because after all, it contains the density matrix of the medium. So there is one more step we can do to actually explicitly separate out the physics, the perturbative physics from the non-perturbative physics, which is to match this S medium down to another function, which will be purely non-perturbative and sit at the scale MD. And that would be equivalent to sort of doing an expansion in the ratio of the temperature to our perturbative jet scale, which is PTR. So this is something I'm still working on. So remember that S medium is in this current form is still independent of the properties of jet, but it does contain both perturbative and non-perturbative pieces, which is why if you really want to sort of exploit the full power of the EFT, you should separate out the perturbative pieces from the non-perturbative, which is something which should be out soon. So after doing all of this, the point is that we can use this framework now to recompute functions, recompute any jet substructure observable over and over again. The S medium needs to be computed just once, and it is a non-perturbative. It contains both perturbative and non-perturbative pieces, but that's just need to compute once. And we have an operator definition for it and everything, and it's independent of what we are measuring on the jet. And you have a jet function, which in this case is perturbative, and hence you can recompute it and do this for any jet substructure observables, as long as it's perturbative, obviously. You can do that calculation analytically. Okay, so that brings to the end of my talk. So what I wanted to convince you is that if we have to make any kind of robust quantitative predictions in a strongly interacting medium, factorization is crucial, and which we have seen lots of times in hadronic collisions, right? So it allows us to isolate the universal observable independent properties of the strongly coupled medium. And hopefully I have convinced you that it's sort of a general framework to compute any jet substructure observable. So it sort of opens up an avenue to sort of explore a large number of other jet substructure observables that might be relevant. And one thing I haven't talked about in this talk at all, because, well, I had only 30 minutes, is how can you actually do this for a dense medium? I can tell you in one line that this kind of factorization can also be extended to the case of dense medium. Obviously, it's more complicated, but as long as there is a reliable separation of scales, you can always do this type of factorization. And if anybody is interested, we can talk about that offline. Thank you.
Thank you very much. That was an excellent talk. Questions?
Hi, I just want to confirm. I mean, if you could look at your page 12, the definition of this medium function you have, and in the operator you have, what is S? S is, you said the Wilson line? Or?
So yeah, S here is the Wilson line. And this
is operator is the same point, right? This precise bar is the same point, or are they replaced?
Sorry, can you repeat that?
This operator, when you have this precise bar,
yes,
are they local operator or they're not?
Yes, this is a local one, and that but there are two.
If you have local one, then you have SS stop.
Oh, there is a TA in between. Yeah, they will not cancel. There is a TA factor in between.
The what?
There is a scalar factor, so they won't cancel immediately.
The scalar factor. What does it mean? The T.
There is a color factor TA in between, right? So S plus and S plus dagger are not going to cancel.
Okay. Yeah, I mean, it's kind of strange because you define it as a sort of like the mean free path, and normally it's that quantity is not infrared. I mean, it's not infrared and collinear safe, and that's why this. Yeah, it is. That's why Q hat came up, and Q hat is, is safe.
Right.
Right.
Yeah. So S medium itself is not an observable, right? It's a function.
No,
like
the mean free path is not. It's not, right?
Yeah. So but this quantity is, which is a combination of all of these pieces, right? Which is your Q hat in general, or even the lambda mean free.
The Q hat is, yes.
Yeah. So all of these pieces, so as you can see, they are also dependent on the renormalization scale. So the observable quantity in both cases is lambda mean.
That's why I'm confused. You equate the Q hat with one mean free path, which is not. I'm just confused.
No, it's not equal. I said it's related to that. There is a difference between them. There is a K-pop square in here.
Yeah, okay. Yeah, but you have equal sign there. That's why I'm confused.
Oh, this is the arrow sign, meaning that they're related. Actually, they are not the same. Yeah.
Okay. Next question to Conrad.
Hi, Varun. Thanks for talks that gives some ideas, but what I'm confused about is how your work is related to kind of the previous talks in today, for instance, where we discussed emergent scales that come up in the medium. When you propagate through it, you have this accumulation, et cetera, So you're still in a small medium length limit, but it seems to me if you go back one slide to slide 10, this form that you have there, this is valid strictly for soft medium emissions. You also have a hardtail of medium emissions, which would basically extend to any energy. So I'm very confused because can you show us how from this very involved, very cryptic formula here, you can get back some known results that we know, for instance, the GLV spectrum.
So this spectrum is basically derived using a very specific hierarchy of scales, right? So you are trying to give a prediction for the production of a jet with a small jet radius, which has a specific hierarchy of scales, which sits like this. So PTR is a scale well removed from PT and well removed from lambda QCD. Now, in this hierarchy of scales, the formula that I have written is exact, and there are no more corrections up to the power corrections in my expansion parameter, and that's all. Maybe I've written that out here. Yeah, so these two will be my expansion parameters. And
but these scales, they don't really appear in the calculation of the medium due spectrum. So I don't really understand. What are you convoluting here? Are you convoluting a vacuum emission, a jet that comes from a vacuum kind of jet, and you add to that the possibility that the jet can originate from a medium induced emission, or what are you actually doing?
No, I'm doing is that the hard interaction happens and that creates a vacuum sort of a jet. And the initial piece is describing for you how the jet evolves in vacuum, so to speak. So if I ignore this piece, that would just be the vacuum cross section, right?
Yes.
And then the effect of the medium is basically captured by this piece, in which the jet is propagating through the medium and interacting with it.
But what does it mean that the jet interacts with the medium? Does it emit something else, or is it just
if it interacts with it? It has all sorts of emissions in it. It has radiative corrections. All of them are included in this lambda mean free path piece, right?
Well, I don't know. That's a quick.
Yeah, that's what I'm telling you. Which is why I'm sort of getting. So the radiative corrections.
If you can go to a limit where you only emit once in the medium, what will you get?
I'll get a BFKL evolution.
BFKL?
That's the leading order radiative correction. So this is this kind of diagrams, for example.
That's a diagram that I recognize from the so-called GLV spectrum, where you have an additional gluon induced by the medium interactions.
Yes, so this is one gluon emission induced. The one gluon emission will lead to a leading order, sort of a leading log correction, which is and when you resum that, that's basically the BFKL evolution. That's what I'm saying.
There's no, what do you mean leading? Yeah, okay, maybe we should discuss there's in principle, yeah.
So I mean, maybe I can give an analogy, right? For example, when I just take,
for instance, this spectrum here is normalized. This diagram is normalized in the beta Hiter limit, and there's no divergence. So, well, there is. Okay, I see. Okay, let's maybe discuss offline. Sorry.
Right. So before, just one comment I'll make, that you can always think back to the case of the PDF, how it works. And you have some radiative corrections which lead to declap, right? And this is the exact analog for that. That this medium function, you can think of it exactly as the PDF for this medium. And the renormalization group equation for that, which includes radiative corrections, is BFKL. That's all I'm saying. Anyway, you can discuss, yeah.
Okay, let's go to Zoom, Abhijit.
Hi, can you hear me?
Yeah.
Yes. Hi. Just can you go back to page 10? I had the same, I think, issues as Conrad,
okay,
to some extent. When you say mean free path of a jet, what do you mean?
Well, what I mean is that when I calculate my cross section, it naturally appears in this form. So there is an object which appears automatically out of my calculation, which I call, which appears as a ratio of these length scales. So if I were to integrate over L minus, that will basically give me something like an L minus over lambda mean free path. So this quantity is not what I'm inventing. It's basically falls out of my calculation, and it falls out of my calculation via this structure. Okay. So if I just compute this to leading order in the opacity expansion, then there is a length scale which automatically emerges written in terms of these functions, which is what I'm calling mean free path basically. Does that answer your question?
Partially. I guess what you're saying is that it is simply a mathematical
It's
object.
simply a mathematical, yes. And which is why it's simply a mathematical length scale that comes out automatically. That's what I would say. In that sense, it's emergent scale for me.
Why do you call it mean free path of the jet?
Because that's the interpretation that I see from this integral. That's all. That it shows to me this is very similar to the expressions that are usually written in literature, right? In terms of computing.
Let me give some idea why it's confusing. When you say a mean free path of a parton, that kind of makes sense, right? You know, yeah, but for a jet radiates partons at all energies, which can interact continuously with the medium. So when you say mean free path of the jet, it's not very clear what that means.
It's a collective interaction of all those partons, right? You have a well-defined notion of a jet which is defined by its radius.
So depending upon how much transverse momentum you think you're exchanging with the medium, that number could be anything.
Yes. No, but the point is that you are imposing some constraint on the jet, right? You are trying to find the probability of isolating a jet of radius r, right? That's the cross section you're trying to compute, which is why whatever transport you have in the medium is going to depend upon that r. That's what I'm saying.
So if the r is large enough, then you will have all sorts of
partons
in the medium.
Again, this factorization is derived explicitly in the regime where r is small and it lies in it's small. So that's where this factorization is valid. So that's why I showed you this factorization in terms of showed the scales, that there has to be a clear separation of scales for this to work.
How small does r have to be?
As long as it's well separated. So basically, the error will be of order r square, right? Whatever expansion you make. So that's what I showed you here. So there is a correction of order r square to this.
I see. What you're saying is if I make the r very small, the jet looks like a parton, and then I can define a mean free path. Okay, I think that I can understand.
Okay.
Hi, Varun. Thanks for the very nice talk. I'm curious of the second last slide you had where you summarized your EFT.
Yeah.
So I think you explained very clearly that at PT times R, you have this two function, the jet function and this medium. Could you repeat what is the other axis, this eta? Like what does that do? And
in this graph?
Yes.
This scale you're saying?
Yes.
Oh, that's basically the rapidity, essentially. So you can think of the medium as being made of kind of soft partons, because they are all at the temperature T and they're moving around. And by soft, I mean they're small compared to the energy of the jet, right? Does it make sense? So you have a jet which is moving in some specific direction, and you have these soft partons of the medium. And if you look at them in kinematic space, you can see that the jet has a much higher rapidity as compared to the medium, the partons of the jet rather. So the K minus over the K plus, essentially. So that's why they are separate. You can separate them out in rapidity in the phase space that they populate. So I didn't want to go into this in detail because I have to explain SCED then, which I'm not going to do because this is based on soft cooling effective theory. But that's the idea, that in phase space, you're going to separate them out, that there is a well-defined region in which the jet function, in which the partons of the jet live. They're highly energetic and moving in a specific direction. And so they have a large rapidity. And the medium is made of sort of the soft partons and soft radiation, which live at small rapidity. So that's the sort of a separation here that I'm showing.
So basically, it's just that soft particles perpendicular to the jet direction.
Soft particles along any direction, in fact. I mean, it's a generic phase space that you occupy in terms of power counting, I'm saying.
Okay, and just this is just a very short question that in the beginning you listed the ordering of the scales, and one of them was the size of the medium. But especially, like, of course, you know, like you have to define 5 different types of effective field theories related to what is the size of the medium, if it's small or short.
Yes. So here, for example, for the case of a dilute medium, I have just 2 cases, as I said. If the medium is long, then the only thing that happens is this scale changes. This scale is different for the 2 cases. So the logs that you resum in your BFKL evolution will change, and that's all that will happen depending upon the size of the medium. This is for the dilute case. For the dense case, it's complicated. We can talk about that later.
Thank you, Alon.
Yeah.
Yeah, hi, Varun. So I have a question concerning the BFKL evolution. So usually BFKL is a function, I mean, it's an evolution equation with respect to, say, log of S, right? That's rapidity. And you resum logarithms of S. And then, of course, there's Q squared, right, or KT. So you'd have like 2 variables. And but definitely in the Regge limit, log of S is much larger than log of Q squared. That's why BFKL is, let's say, the appropriate evolution equation as opposed to DGLAP. So in this case, so what would be the collinear logs? So I understand it would be like log of KT, right?
You mean the logs resummed by BFKL? Is that what you're asking me?
Yes, exactly. So you mentioned it briefly. So what would be the log that's resummed here in this equation?
So this log is basically these types of logs, which I'm showing right now, which is alpha s to the power n log to the power n of nu j over k pub. So KT is basically the KT that is interchanged between the jet and the medium. And nu j is basically the jet scale, and that, as I said, depends upon actually the size of the medium. So if the medium is long, then you can assume sort of, as I said, that the jet has enough time to form before it interacts with the medium. And then in that case, the jet scale is just the PT of the jet, or you can say the energy of the jet. Whereas if the medium is small, then because of quantum interference, actually the scale is actually much reduced, and it depends upon the length of the medium and the formation time of the jet and multiplied by PT. So you can see that the scale is reduced because in this limit L minus is much smaller than TF. And so the log will also be correspondingly be small then in that case.
Right. So I'm a little bit confused because we've analyzed this logs in for dense medium, but for high KT. And I naively think that when I have a large momentum transfer, that would be kind of similar to the dilute regime. And in addition to the log of KT, so we get, of course, log of you'll have 2 regimes, as you mentioned. One regime would be log of the length of the medium, and then another regime which is very high KT, that would be log of 1 over x, x being Feynman x, which would be related to, as you seem to say here. I try to connect. And
right. Yeah. So this is sort of the log of x that you see in the small x DIS, right? It's similar to that. Yeah.
Right. So the question is whether that log is indeed, have you checked that log is much larger than log KT over than the collinear log, so that really you are in the regime where the Regge limit rather than say the double log limit, or because that's what we've been saying for years. The evolution of jet quenching is in the double logarithmic limit, which is kind of diagonal because the 2 logs are similar. And then you can use you can use BFKL, but you can also use DGLAP. Simply, it's just tending to the same limit from different directions, but it's not exactly BFKL, so to speak, right?
Well, I would argue that it's exactly BFKL, and you are right that the double logarithmic time thing is contained in the BFKL, so that's automatically contained in this one. So I could take that limit.
Yeah. Man, I'm not saying the approach is not appropriate.
No, the physically intuitive thing I would say is that we are relying on the fact that the partons in the medium are going to have a forward scattering with the partons in the the partons in the jet are going to have a forward scattering with the parton in the medium, and that is determined essentially by the fact that that we have that R is much smaller than 1. So this R basically is the angle of deflection, right? And that by definition in our hierarchy is small. So that's why the forward scattering limit and hence the Reggie limit is the one which is more appropriate, is what I'm saying.
Maybe we can take this offline. I mean, it's just a subtlety here. I mean, it's not yeah. Okay, thanks.
I have one question actually coming more from the experimental side. So what aside from the extension to dense medium, what if anything is missing from the theory side before we can test this factorization that you write down and also extract this medium PDF?
Nothing. So you need to extract the medium PDF. The only issue I can think of is that obviously, unlike the case of hadronic collisions where you create this, where the parton, where the hadron is exactly the same every time you test it, the medium is not going to be the same in every event. So in some sense, even though this is a universal operator, the rho will change from event to event, right? So in that sense, there will be some average rho maybe that you could put in here. And if you do find that average rho, maybe you could compute this on the lattice and make a prediction, or in some sense extract it. Otherwise, there is nothing left here. Okay, the thing that's left here is to do this, to do the second stage of the matching, to actually separate out completely the non-perturbative physics. So that will yield an operator which is similar to what I have right now, but maybe slightly different because it's a different operator, because it's at a different scale. But this step of matching needs to be done, I think, which is what I'm working on. And then there is nothing else. You just have one medium PDF and you can make a prediction for a perturbative jet observable and extract out the PDF, extract out this medium PDF. That's all.
Yeah, I just have a very basic question. So what do you mean by jet PT here? It's for sure not the experimentalist jet PT, right?
It is, right? It's the total part of PT of the jet.
Yeah, but well, in the so this is from one of the hot scattering, right? So it's not like so suppose you have multiple scattering, then the jet PT is not really what you're referring to here, right?
No, it's still the jet PT. This is the hard scale of the problem. The point is, this is I have had a discussion before, but it's like you sort of take those things into account when you say that. You are right in the sense that when the medium interacts with the jet interacts with the medium, some of the partons will go out, so the PT of the jet will change, right? Yeah. So this is sort of the final PT of the jet. That's what I mean by PT.
But you can also have multiple scattering which create a high PT jet, right? So
sure. So yeah, I have not talked about multiple scatterings in this case, but you can do that as well for dense medium. Yes.
How do you do that?
Basically, you have to sum this series. So right now I have shown you that this is sort of the first term in the series. So this works if I can stop at this point, if this condition is valid, that is when the medium is much larger than the medium is much smaller than the mean free path. But if they are not, if the medium is dense, then these two scales can be of order 1, and then there is an entire infinite series that you have to resum. And there are different regimes of it. For example, in the Bethe-Heitler regime, as mentioned in the previous talk, it just exponentiates the series. When on the other hand, there are other cases where the mean free path is comparable to the formation time of the jet and which are much smaller than the size of the medium, then you have LPM effect. So that's a different regime of the EFT, which leads to the BDM-PSZ formulation. And then the third one in which the formation time might be much larger than the size of the medium, in which case you actually have a BK type equation, again similar to DIS at small x.
Maybe it's just it's just because of my background knowledge, but I just wonder, so suppose you have 2 parton scattering, so it produce 1 jet, right? So compared to 1 scattering, you also can produce another jet with the same PT. But in the case of double scattering, you can have, for example, median recoil, right? So which happen to create a hole around the second hot scattering. And then this factorization will now be working, right?
You mean the recoil of the jet? I mean, I maybe I didn't understand your question, but by recoil of the jet, you mean that there is some interaction of the jet with the medium? Is that what you're saying?
Yes. So for example, what you presented here is that you can factorize out the jet PT, right? So this calculation, but in reality, when you have median recoil from another scattering, then that's not included in your calculation.
Yes, for now, if there is some, no, it's not. I agree. It's not. If there is some other independent hard scattering that happened somewhere and there was some recoil from that on this, yes, that's what included in this.
Okay, thanks.
Okay, let's thank Varun once more.